In the case that we have springs in parallel attached to the same mass, then if there's a spring constant for one spring of K1 and a spring constant for the other spring of K2, then the effective spring constant is just the sum of the two. If we have springs in series, so they're attached one end to end, and one spring has a constant of K1, another has a constant of K2, then the effective constant for the entire system is K1, K2 divided by K1 plus K2. Once you have all those numbers, you plug it in for K, and then it proceeds as we saw in the previous example. For damped motion, so this would be when you have a spring mass system in a medium that's providing resistance to motion, like a piston in oil or something along the lines, where the environment is imparting another force. Then we have m d2x dt2 equals negative kx minus beta dx dt. The m dtx dt2 is mass times acceleration as before. Negative kx is the restoring force from the spring. And the negative beta dx dt term indicates that the damping force is proportional to the instantaneous velocity. The constant beta is a damping constant. This equation becomes d2x dt2, and what we're about to do is divide both sides by m and then bring everything to the left-hand side, plus beta over m dx dt plus k over m x is equal to 0. As before, we're going to let omega squared equal k over m, and we're going to let 2 lambda represent beta over m. Why 2 lambda? You'll see. Then our equation becomes d2x dt2 plus 2 lambda dx dt plus omega squared x is equal to 0. The auxiliary equation has roots of r equals negative 2 lambda plus or minus the square root of 4 lambda squared minus 4 omega squared divided by 2, which simplifies so nicely. R turns out to be negative lambda plus or minus the square root of lambda squared minus omega squared when the radical and fraction are simplified. This leads us to 3 possible cases. Case 1. This is when lambda squared minus omega squared is positive. And then the equation of motion is x of t is equal to c1 e to the negative lambda plus the square root of lambda squared minus omega squared t plus c2 e to the negative lambda minus the square root of lambda squared minus omega squared t. This type of system is overdamped and does not oscillate. Basically, the medium is preventing the mass from moving back and forth. Depending on what C1 and C2 turn out to be, this could just be taken from equilibrium and then move back toward equilibrium, or it could be taken from equilibrium, bounce once, and then come back to equilibrium. In other words, it's never going to cross equilibrium more than once. Case 2 is the case when lambda squared is equal to omega squared. This doesn't happen by accident. You basically have to work real hard to make this happen. But if it ever did, then x of t is equal to c1 e to the negative lambda t plus t c2, or I should say c2t e to the negative lambda t. You can think of this as like a delineating case. You've got case 1 where it's overdamped. This one's called critically damped. And again, the system could cross equilibrium at most one time. I said it's a delineating case. It's really what would separate case 1 from case 3. In case 3, we have lambda squared is less than omega squared. And in that case, the square root of lambda squared minus omega squared is imaginary. And so we're going to write that as the square root of omega squared minus lambda squared times I. The equation of motion in this type of system is going to be x of t is equal to e to the negative lambda t times c1 cosine of, we'll write it as omega squared minus lambda squared to give us a positive number in there, t plus c2 times the sine of omega squared minus lambda squared t. And because of the presence of the sine and cosine, this does oscillate. And because of the e to the negative lambda t, lambda is a positive number, it oscillates with a decreasing amplitude. So a picture for a system like this might be oscillating, but then getting closer and closer to equilibrium. I didn't draw that right, because the period shouldn't be changing as it gets closer and closer to equilibrium. This one is called underdamped. Finally, we could have a forcing force, if you will, represented by f of t on the right-hand side of the differential equation. This is the non-homogeneous case. This is called driven motion, and the auxiliary equation is solved as before. And if that right-hand side isn't 0, then we're using undetermined coefficients or variation of parameters.